Swayam Prabha. Digital India. Educated India.
Yeah, so we are talking about this instantaneous center velocity. So where we said that the idea here is that so there is a point, there exists a point say C which has 0 velocity, and so that means that say given the velocity of A and omega, so we have shown just a minute, it goes the other way. I could have put it this way also. I could have, it would have gone out, no problem. So what we said that VA given, so then our construction is so locate C on line perpendicular to the A at a distance. This is D, let us say, equal to VA by omega. So that way we can very easily see, if you want to find out the velocity of C, it is and so graphically we can see that if you want to get the velocity of C, so velocity of A and on which you add omega times D, and these two together will be so obviously this is omega D, and these two put together VC will be 0. So you can see that AC is equal to VA by omega. So that way we can see that VA minus VA is equal to 0. So this is how we can locate. So this is what I've done last time. And the advantage of this one is that once you locate C, then the whole velocity analysis will become very simple. So that means that if you want to, so once let us say, if you know C location, so any point B here, for example, any point B here, so will be simply the distance CB times omega. So that is, so the distance, the velocity here the magnitude is omega times CB, and direction is perpendicular to BC. Okay, so that way the whole of our analysis will become very simple. And so this is knowing VA and omega. But on the other hand, many times we know VA and we may not know the omega, but we know the direction of another velocity of another point. So then again, we know that it is going to lie on lines perpendicular to these velocities. So what I mean is that, so the other method is that locating C if two velocity directions, say of VA and VB are known. So it is simply draw perpendicular to VA and VB, and intersection is C. So this is intersection is C itself. So in one of the simple examples, so for example, so there are if you know the velocity of A, and obviously you know the direction of velocity of B because they are guided, and we can locate the instantaneous center on two lines perpendicular to A and B. So this is nothing but your C. The intersection point is nothing but C. So interestingly, if you know the location of C, then the whole velocity analysis will become very easy. So for example, if this is L and this is theta, so if VA is given to you, then the omega, okay, omega of the rod is nothing but VA by AC, and this is nothing but VA by L sine theta. So at this particular instant, so the C is located whose angular velocity is omega is like this, and once you have that, the velocity B can be simply said that omega times BC, and this is nothing but this times BC. So BC is nothing but, I think I'll leave it, the substitution of omega. So okay, so this is how you can calculate the velocity of B. For that matter, you can even calculate the velocity of any other point. Okay, so any other point, for example, if you have a point here, and if you want to say this is some point D, this is some point D, so it is nothing but the velocity of D will be like this. So it is simply omega times CD, and it's in direction perpendicular to this line CD. Okay, so this way you can find out the whole velocity analysis in a very short time. Okay, so this there are several aspects of that which we are going to talk just now. a few other examples is the rolling of a wheel. Another example of rolling of a disc. This you have done, but from the concept of instantaneous center, so if you know the velocity of A like this, so in fact we know that you know that the point C has a characteristic that it's 0, velocity of C is 0. In fact, that is the premise on which we have started, saying that the disk is rolling without sliding or without slipping. So it is starting. So you can see that then the C here is nothing but having a 0 velocity, and it is an instantaneous center. So once you know, obviously we know that omega is, say, VA, or if you want, you can even say V0 divided by R. And if you want to know very easily that if you want to know the velocity of this point B, so it is nothing but it is in this direction, and it is equal to omega times twice R, 2 omega R, or you can even say that it is twice V0. Very simple. For that matter, you can even locate some other point D here. If you want to know the velocity of D, it is simply like this, perpendicular to CD, and in fact, if this is some 45 degrees, so we can very easily find out. So it is nothing but omega times root 2 R, and omega R is V0. So and obviously it is, if it is just 45 degrees, so this is also is 45 degrees. So like this, we can find out the velocity of any other point. Any other point like this, for example, will be like this. So this is a very fast way of calculating, and it also gives us a good insight into the various velocity analysis. So I'll just take another, there are so many examples. Another very often used example is the crank and connecting rod. So this is for one body. So each body has an instantaneous center. So if you look at another example of crank and connecting rod, take this example. I don't call it C because C may interfere with our nomenclature of instantaneous center. So if you have A, B, D, and if you know that this is going at an angular velocity of omega 1, and so let us say this is theta, you know how to calculate all these things. So if this is R, this is L, we know how to calculate phi. The configuration you know. So for AB, the instantaneous center obviously is very clear. The point A is having 0 velocity. So A is the instantaneous center of, say, AB. So say, let us say 1, I see 1, if you call this as 1 and this is 2. And for link 2, that is the connecting rod, where is the instantaneous center? Of course, once you have the instantaneous center, this is very trivial. The velocity of B also can be calculated. This is velocity of B. So velocity of B is simply, it is perpendicular to the crank, and it has velocity of omega 1 times the radial length r, AB. Okay. So where is the instantaneous center for link 2? So the instantaneous center for link 2 will be, obviously it's not A. So what we know for AB, for say BD, so we know the velocity of B is given. I mean, we found out from analysis of crank. And what about, we know also that velocity of D is like this. And so since we know the two velocities, directions at least, so then we can find out the location of this one. One is, line is drawn like this, okay, perpendicular to this, and this is like this. So the line perpendicular to that is nothing but an extension of the crank. Okay, this is perpendicular to this. Obviously, it's an extension of the crank itself. So this is C2. So if you call this as link 2, and so C2 is the instantaneous center for link, the connecting rod. So it is VB is perpendicular to this, and then now we have to draw perpendicular to that. So it's nothing but an extension of this line, and then there's a vertical line here because this is horizontal. Okay, so like this. So where is it located? So the location of that is very simple. Say for example, so what is the this distance? Say distance D here is, let us say, how much is the distance D? Is nothing but R cos theta plus L cos phi. Okay. So if that is the case, then what is the distance C to D? So this is equal to, how much is that? So it is D tan theta. So this is D tan theta, right? And then this distance, so this distance is, how much is that? It's D by cos theta minus R. So I need the distance only, the B to C2. Okay, the total distance is D by cos theta and minus R, so that will give me this distance. So the rest of the analysis just follows very simply, is that what is the angular velocity of 2? Okay, so because you can see that now this point is moving like this point is moving like this. So essentially the whole connecting rod is rotating about the instantaneous center C2. Okay, so how much is omega 2? So omega 2 is nothing but, say, VB divided by D cos D by cos theta. This is omega 2, and VB is known to be, is nothing but omega 1 times AB. So that is known. So once you have omega 2, so then the rest of the thing is, if you want to calculate velocity of D, the magnitude of velocity of D is nothing but omega 2 times C2 D. Okay, so that way this velocity analysis turns out to be very, very simple. Okay, so this is one single body, whereas this is two bodies. Actually it's four bodies. So it is, when you have more than one body, you have instantaneous centers for each body. So instantaneous center for AB is nothing but A itself. Instantaneous center for the link 2, that's a connecting rod, is C2. And from the known omega 1 to you can go to VB, and from VB you can calculate the angular velocity of 2. Once you calculate the angular velocity of 2, then you can get the velocity of D. Okay, so this is a very systematically you can go. You can find out many examples, absolutely many examples where you are supposed to find out the instantaneous center so that the velocity analysis will become simple. In fact, for velocity analysis, we have been doing many methods. So you should be conversant with all the methods. Once you are, expert in all these methods, maybe you can choose whichever is convenient, whichever is okay. So like this, so we can do this. Interestingly, there are a couple of few others. Is the thing known as, well, there are so many examples. For just I tell you another one simple example before I move on. So this is rod testing on a wall and sliding. So AD is a rod on a staircase kind of thing. So can you find out where is the instantaneous center for this one? So it's one thing is that, so you have the velocity of A here. So it is on a line perpendicular to this. Okay. And where do we know anything, any other velocity information? So any other velocity information. So if you look at, we keep saying this one. So for example, if you take a B prime on the rod, okay, on the rod, but just opposite to the top point, okay, on the vertex here. So this B prime is a point on the rod, but right here, just next to this support point. Okay. So do you know anything about the velocity of B prime? How is B prime moving instantaneously? See, all these things, as I've been telling you, these are instantaneous centers. So these are valid only at that point, and that point may change. We're going to discuss that very soon. So what is the velocity of B prime? So it can be the other way also. Giving the rod AD, assuming that AD is your rod, how is B moving? Okay, with respect to the rod AD, how is B moving? If it is allowed to move, okay, the rod is fixed and B can only move along the rod. B can move only along the rod, right? Right. So now you can even reverse it. You can fix B, and we can say that at this point the rod will be moving in which direction? So the rod, the point B, will be moving in this direction. Okay, so the VB prime is like this. So this is B prime, and it's in this direction, right? So this is what you have to realize, because B has to move with respect to B prime along this direction. Okay, so the reverse is also true in the sense that if B is fixed, so how is B prime going to move? So obviously it can move only in this direction. So if that is the case, then it is, so this is, we draw a perpendicular line here to VB prime, and this is where the instantaneous center C is. Okay, so once you understand these, how the velocity directions of 2 points, and then you can always locate. Once you locate it, then you can definitely find out what is the distance and so on by simple geometry. So let me just quickly give another 2 points. So if we go back to this example of so we know that the instantaneous center C is located here. What will happen a little later? Another configuration. So in another configuration, so let us say if it comes here and this will be moving here, and then the location of this one, say let us say B prime and A prime. So where will the center will be? So center will be is on this. So this location of this C is going to change. So that is why this is called an instantaneous center. So the location of C changes from one configuration to another configuration. So this is what you have to realize. So that is why it is called instantaneous center. Since the location is going to change from one configuration to another configuration, so it is called instantaneous. So if it has velocity, so we can even say at each time instant the C is going to change. So even the velocity analysis keeps on changing from one configuration to another configuration. Okay, so there are a couple of things here. So the locus of C okay, in space sorry, locus of C in xy space, well this is x, well xy space means this is the fixed space. Okay, so locus of C in xy space is known as space centroid. So it is a line on in the space, and what is that locus? Can you tell me what is the locus here? The locus of the C, is it a straight line or is it some kind of curve? And if so, what is that kind of curve? See what happens here, the extreme position. So let us say if you go to the extreme position, so the extreme position, so when the rod comes here and it is lying here. So let us say this is A double prime and B double prime. Where is the instantaneous center? It is just, let us say it is just about to touch the point, about the ground. So where is that, the instantaneous center? So here A continues to move like this and B continues to move in the vertical direction. So where is the intersection point of these two? So the intersection point of these two is a perpendicular line here and a perpendicular line here, and this itself is C double prime. Okay, the perpendicular line to this one goes along the rod itself, and the perpendicular line here goes vertically here. The intersection is this itself. So that means that in the x, so this is the limiting point. So similarly here, maybe I'll draw here just because of So this is a distance of L, and similarly at a distance of L, this is the limitation. So where is it located? So at every point, do you know what is this various locations here? So this is nothing but a quarter of a circle. Okay, this is nothing but a circle here. So you can very easily prove it. So if this is some angle theta, so if you call this as C, the x coordinate of C is nothing but, what is that? L cos theta, and y coordinate of C is L sin theta, and we can see that this is x by L square. So if you eliminate theta, so this is what you get. So this is nothing but the circle, okay, quarter of a circle whose center is here at the origin. So this is how the center moves. Another term which is related to this one is space centroid, is the locus of C in xy space. There is another locus. So locus of C on the body. On the body, I'll just explain it. So this is called body centroid. So what we mean by this is that this is the space centroid, which you know it, and body centroid is that, imagine that you have a big cardboard here, big cardboard on this okay. So if you have a big cardboard fixed on this one, a rectangular cardboard, and then if I locate the locus of C on the board, so what will be that? So that is known as the body centroid. So the body centroid, so how do we locate that? What is the kind of locus of that? So any idea? Can anybody tell me what is the? So that means that, so after marking all this C there, so if I just take it out and I take this, okay, rectangle, and I have points. I have these points located on this body. So what will be the locus of that? Okay. Interestingly, it will be another circle. How do we prove it? So let us say this is with respect to the body. Okay. So that means that we have to create a so now consider so I will erase this. So for body centroid, consider x prime, y prime axis fixed to the body. So like this, so this is x prime and this is y prime, and we had to find out the location of C with respect to x prime and y prime. So how do we get the coordinates? So this is the coordinate here, say some point P here. So BP So x prime c is nothing but BP. Okay, and how much is that? So this is L cos theta. So this is also theta. So L cos theta and cos theta, L cos square theta. What about the coordinates of C with respect to the pi prime coordinate system? So it is nothing but CP, it is L cos theta sin theta. So we can eliminate theta from these two by a little bit of trigonometric manipulations. So L cos theta can be written as cos 2 theta okay, and y prime sin theta, so it's L by 2 sin 2 theta. So you can guess what I'm arriving at. So you can see here that this whole thing will boil down to xc prime minus L by 2 pi L by 2 okay. So it's again the equation of a circle of radius L by 2 and its center is located at L by 2 0. So that means that it is so if you take out the board and then if you look at how it is located, so it is nothing but a circle, so which is at a distance of L by 2 and
plus hello sir. Sir, it is
Sorry?
xc prime plus L by 2.
Right, thank you, that's right. So it's yeah, that's right, it's not -1, it's +1, so I'll continue to have -1.
Very good.
Yeah, thanks. Yeah, so that way, so that means that the body centroid, if I just draw it, it is also a circle and it is a semicircle drawn on AB, whereas the space centroid is a quarter circle drawn with a radius of L. Okay, so interestingly, so as the motion takes place, so I'll just draw this. So there are two circles. So one is a bigger circle, space centroid. Another is a smaller circle, which is called the body centroid. So it can be proved that as the motion takes place, the body centroid rolls. Okay, so the body centroid rolls on the space centroid. Okay, so I think maybe at some point later, maybe you can see that. So the body centroid rolls on space centroid. Okay. So all these things can be proved just as analysis which we have done. So this is a disk rolling on a horizontal ground. Can you tell me where is the space centroid and where is the body centroid for this one? So the bottom point here is the space instantaneous center. So as it rolls down, so the ground here, say LM. So LM itself is the space centroid. What is the body centroid? Body centroid is nothing but the periphery of the circle. Okay. So the periphery of the circle is the circle is so these are some interesting offshoots of this body centroid. So then if you go to 3D, then these are surfaces, body centroid surface. Here these are only lines, and then there are surfaces. In fact, here these are very simple straight lines and circles, but it can be the complex curves. And one last thing before we finish up this instantaneous center is that is it also instantaneous center of acceleration? That's number one. Okay. Is the acceleration 0? Is instantaneous center? It's only velocity is 0. So instantaneous center here of velocity is 0. V of IC is 0. But acceleration is not necessary to be 0, and it will not be 0. Why? Can you simply say that acceleration is not 0? So it is because the center is changing its location, right? It's going from one location to another point, even whether it is space centroid or even the body centroid, it is changing its location. So which means that instantaneously it is having a 0 velocity. It will gain velocity after an instant because there is an acceleration. Okay. So that's number one. Number two is such a center exists for acceleration? It may not be the same center. Okay. So the question is that is such a center, such a point exist for acceleration? Yeah, maybe, yes. Yeah, you can always find out some point in the body which has 0 acceleration. Okay, but what will it be helpful for us? Say if you, in the case of velocity, if you know the center is here, so we simply put the velocity omega times a, so to get the velocity of a. But if you have, let us say, it's a little cumbersome and difficult, maybe it's not impossible. So where there is some point B here where acceleration of B is 0, maybe. Okay, so will it help you in any way? So if you want to locate another point here, can you simply say that it is perpendicular or it is like this? No, you cannot say anything. Okay, so there is a normal component, there is a tangential component, tangential component, normal component. So there is no way that it's going to help you in any manner. Okay, so it's not going to help. And because there's a normal accelerations, there's tangential accelerations. So neither can you say it is only along the line or perpendicular to the line. You cannot say anything, and there is no point in doing that. Okay, I have just 2 minutes. I thought I will take another. Now I have to do one acceleration problem where we have rotating frames application will come. So there are points which are moving along the rod, not as a hinge. It's no more a hinge, it is a slider on the rod which I have to do. But I have just 2 minutes. I'll tell you another here is that I'll just take 5 minutes. So, okay. So in the sense that, so velocity image, what do we mean by this? So if I have, say, 3 points, let us say A, and I know the velocity here. Interesting. So I have, this is velocity diagram. I have 3 points on the body, and then I've drawn the velocity of B, velocity of C, and velocity of A. And obviously in the diagram, so you can also find out the direction and magnitude. If you actually draw it to scale, you can actually measure it to the scale. So the one important thing here is that I wrote small letters ABC just to show the velocity images. So can we prove that delta ABC is similar to delta ABC? Can we prove it? Quick, okay? It's not impossible. For example, AB here. So the vector, so let us say the magnitude. The magnitude of this one, what is AB? So the vector AB is nothing but the velocity of B with respect to A. So this is nothing but, and how much is this? So this is nothing but omega times AB. Magnitude wise, so AB is nothing but velocity of B with respect to A and omega AB. So similarly, you have the BC here is nothing but C with B, and so similarly CA. So what does that mean? So that means that in the velocity diagram, so the sides AB is proportional to AB, and BC is proportional to BC, and CA is proportional to CA. So that way, so this is true. So that means that if you have so what is the outcome of this one? If I know the velocity of A and B, if I know the image of A and B in the velocity diagram, I can locate C. So by drawing a similar triangle. So I have ABC like this one, I have ABC like this one. So I locate C and I can find out the point here. So this is true at many things. In fact, this is also true for acceleration. So I leave it to you. For acceleration analysis also, if you draw the image in acceleration diagram, is similar to actual geometry. You understand? Okay, so this also can be proved for acceleration. So a quick one is, just take, say for example, if you have So if you draw the acceleration, so the velocity of this one is like this, and the velocity of B, I'll mark it A and B, and this is origin. So AB is an image of this one, right? Sorry, did I draw? And AB is not like this. Sorry. So VA, and here this is down. So if I have, say, something like another plate attached to this one, DE like this one, can I draw that image here? So it is nothing but, can you draw where it is? Shall I draw this way? Or shall I draw this way? Okay. So we have to draw it this way. Okay. This rectangle is similar to this rectangle, and it has the same sense. So if it is counterclockwise here, this also should be having same counterclockwise. If you want, you can do. So this way, once you draw the triangle, so then it's very easy to say that this is the velocity of D. Okay, it's very clearly. So this is the image. Okay, so please, so some of your questions in the tutorial or homework are based on this one. So an extension of the body is there. You are supposed to find out the velocity of that. So very clearly, if you want to know the velocity of the center point here, where is it? So it is nothing but the center point here. If you have a center point here, so it will be the center point of image as well. Okay, I think we'll stop here.